This lecture will be the final one for Chapter 8. It's going to be covering the 5 general types of reactions that occur. Now there are other types of reactions that occur, but for first year chemistry we're just going to cover these 5 main types. The first type of reaction that we cover is called a decomposition reaction. It's a reaction that breaks apart one compound into simpler substances. And the simpler substances are usually 2 elements if it's a binary compound, or an element and a smaller compound than you started with. The general form looks like this. AX yields A plus X, where A is typically a metal and X is a nonmetal or some anion. And here's the first example we look at. We break apart water into hydrogen and oxygen. And the hydrogen is a Hunkelbrief, it's diatomic, and oxygen is a Hunkelbrief, it's diatomic. So instead of just breaking it apart into H2 plus O, it actually breaks apart into H2 plus O2. In the next example, we have KClO3 breaking apart. And for this example, we need to have a metal and a nonmetal staying together on the left side, or I'm sorry, on the right side of the yield sign. So we're going to have KCl staying together. K has a positive 1 charge, Cl has a negative 1 charge, so the formula for this compound is just KCl. That's potassium chloride. And then the oxygens are left over. Now oxygen is a diatomic element, so it's going to break apart into O2. Now a lot of students try to make it O3, which is ozone, and that's an unstable compound to form, so it's actually going to break down into O2. Now if you're concerned about the number of atoms on the left side and the right side of the yield sign, you could always balance the equations, and that's what we did in quiz number 2. Now I don't balance any of the equations that we're completing in the 5 general types of reactions lecture, so if you're freaking out about the number of atoms on the left and the right not being the same, we could always fix that by balancing it. So I put a reminder up here that Hunkelbrief means that the elements are diatomic when they're by themselves. So if you have hydrogen by itself, it's going to be H2, or oxygen by itself, it's going to be O2. On the next slide, I'm going to expand this idea of decomposition reactions into 5 compounds that we break apart, and typically these compounds are broken apart just by heating them up. So the first compound that we're going to decompose is called a carbonate, and a carbonate always breaks apart into a carbon dioxide molecule, and if you look at what elements are going to be left over, you're going to have the metal in front and you're going to have an oxygen left over to bond with that metal. So when you break apart calcium carbonate, CaCO3, you're going to take the calcium and stick it to an oxygen, and then you're going to have the carbon stuck to an oxygen. So you're going to have calcium oxide and then of course the carbon dioxide gas. So if you heat up a carbonate, it always makes carbon dioxide. And then there's going to be oxygens left over for the metal. And you don't have to worry about balancing this equation because it works out perfectly, and the charges on the calcium and oxygen are both +2 and -2, so they cancel out. So you don't have to worry about crossing charges. In the next example, we have our good friend the chlorate. We've already broken one apart already. So you basically could think of it as karate chopping the compound in half after the chlorine. So you get NaCl, which is called a metallic chloride, and then you get the O3s turning into O2. And again, if you want to balance it, you could with 2, 2, and 3. Now, the next compound that you're going to decompose is a hydroxide. Now, hydroxides have O's and H's, and I tell the students to think of the O's and H's as trying to stay together as a water molecule. And just like we had in the carbonate, there's going to be an oxygen left over for the metal in front. So the magnesium sticks to an O, and then you have hydrogens and oxygens making water. And the magnesium is +2, the oxygen's -2, so the charges work out fine, and you don't need to worry about balancing this equation. In letter D, we have an oxyacid. Now, an acid always has hydrogen, and because it's an oxyacid, it's going to have oxygen. So just like we had with the hydroxide, the H's and O's try to stay together. And just like we had with the carbonates and the hydroxides, there's going to be extra oxygens left over for, in this case, a nonmetal. So the hydrogen's going to stick with oxygen, and in this example, the sulfur is going to stick with oxygens as well. If you look at how many oxygens are left over after making the water molecule, there's 3 oxygens left over in this example, so the formula for the oxide is going to be SO3. So one of the O's goes with the hydrogen, and then the rest of the O's stays with the other element, which in this case is a nonmetal. If you have a binary compound, it's probably the easiest to understand. You just break it into the pure elements sodium and chlorine, and in this example we have chlorine that's diatomic, so it has a little 2, and again, if you want to balance it, you could. Now every time you try to write the formula for a new compound, you need to make sure you're looking up the charges of the ions, and then you have to cross them if they're different. So in the carbonate, chlorate, and hydroxide examples, we didn't have any charges to cross because they ended up being electrically neutral, so they were even in the positive and negative category. But if they are different, you need to make sure you cross them, and you need to worry about balancing it only after you get the correct formulas written first. And once again, don't forget about the diatomic elements, the Hunkelbriefs. Now the second type of reaction is called composition. Now your textbook, I believe, uses the term combination, or some books use the term synthesis. But basically what you're doing is you're taking two things and you're sticking them together to make one thing. So it's a reaction of two substances, typically a metal and a nonmetal, and it forms one compound. So it's the opposite general form as the decomposition reaction. And the same categories apply that we just looked at on the previous slide, like the carbonates and chlorates, etc. You just need to run the reaction in reverse. So our general form looks like this. Substance A plus substance X turns into compound AX. Now the first example is the element aluminum bonding with the element chlorine. And these are just two elements, and so this is categorized as a binary compound that we're going to make. So you put the symbol for aluminum next to the symbol for chlorine and you cross the charges. And aluminum happens to have a +3 charge, chlorine has a -1 charge, so the formula for this binary compound is aluminum chloride AlCl3. And again, you could balance it after you're finished writing the correct formulas. In the last example on this page, we have lead oxide plus water. So this is a metallic oxide thrown into water. Whenever you throw a metal oxide into water, it makes a hydroxide. So this is a hydroxide category. And if you look on the previous slide, you can see that hydroxides break apart into metallic oxides in water, so it wouldn't surprise you if you threw a metallic oxide into water, it would turn into the hydroxide. So these reactions are reversible. Now, lead goes first, and then the hydroxide group goes second. Now, lead has a +2 charge in this example, so we need two hydroxides to make the compound neutral. So that's crossing the charges. You don't have to worry about balance in this example because it works out perfectly. That's why I picked it. On the next slide, we do the third type of reaction, which is called single replacement reactions. And it's a reaction between one compound and one element. And you're going to do a little switcheroo of the elements, and so you'll get a new compound and a new element by itself. So here's the general form. You have the compound AX, you throw in substance Y, and substance Y represents a nonmetal in this example, and so it's going to replace the element that was in the compound that was a nonmetal. So elements Y and X switch, and then element X is going to be by himself. And if you look at a little spherical representation of it, you can see the colors switching around. In the next example, we have the compound AX again, but this time you're going to be throwing in element B. And element B is a metal, so element B is going to try to switch with element A, which is the metal in the compound. So the cation A and the element B are going to have the same charge. They're going to be positively charged so they can switch. And so you're going to form the new compound BX, and you're going to get the element A by itself. And so you can switch the back halves of the molecules, or you can switch the front halves of the molecules. So that's what the general form looks like. Now the element that's trying to replace the other one that's in the compound already, the one that's by itself has to be more reactive than the one it's replacing, and you have to use what's called the activity series to see if the reaction will happen, and that activity series is going to be shown on the next slide. And the activity series basically just lists the elements from highest activity to lowest activity, or lowest reactivity, I guess I should say. So the higher up you are, the more reactive you would be. Now, there's a special situation that occurs whenever hydrogen is bonded to oxygen in the compound water. You have to be very, very active to break a hydrogen away from the oxygen. It's a very strong connection. So you have to be from the element lithium to the element sodium on our activity series in order to kick out the hydrogen-oxygen bond. So let's take a look at the activity series and I can explain a little more. So here we see the metals listed. Lithium's at the top and gold's at the bottom. So lithium is the most active metal there is. So if lithium is ever thrown into a solution where there's a compound that has the elements potassium or calcium or sodium or magnesium all the way down the list, lithium will actually kick out that metal and bond to the nonmetal. So lithium becomes part of the solution, and then that one element will come out of the solution. And then if you look at the halogens, these are the nonmetals. Fluorine is the most active nonmetal. So if you throw fluorine into a situation where there's a chloride ion or a bromide ion or something like that, the fluorine will kick out that element that's below it, and then that element will be by itself. So it will form elemental chlorine, and then the fluoride ion would go into the solution. All of these reactions that are on the single replacement category will be in aqueous solutions. So let's take a look at some examples, and it'll make a lot of sense. So here we have the element fluorine. Now element fluorine is a nonmetal, and so it's going to try to replace the chlorine. And it can successfully replace it because it is higher up on the activity series as we had on the previous slide. So the switch is made. So now sodium is going to be bonded to the fluorine, and chlorine is going to be by itself. Now chlorine is never really by itself because it's a diatomic molecule, but it's still the pure element chlorine. So the switcheroo occurs. Now why isn't it NaF2? Well, the compound NaF has no subscripts because sodium is +1 and fluorine is -1. So the compound is electrically neutral as NaF. So you got to make sure you cross the charges when you make a new compound, and again look for Hunkelbriefs. In the second example we have potassium. Potassium is a metal, so it's going to try to switch with the other metal, which is iron, and potassium is higher up than iron, so the switcheroo can happen. And so we have K bonded to the Cl, and we have iron by itself. Now again, you won't have a subscript 2 on the chlorine because the potassium only has a charge of 1 and chloride has a charge of -1, so the charges balance out. If you're worried about the number of Cl's on each side of the equation, you could balance it with coefficients in front, but don't mess up the subscripts because they're correct as written. The next example we have zinc trying to replace the hydrogen, and it can successfully replace it. It's in an acid environment, so zinc can kick out hydrogen when it's in an acid. If it happened to be in water, it couldn't break the hydrogen-oxygen bond because zinc isn't in the top 5 or the top 4 or whatever the activity series shows on the previous slide. It's not in that high activity range. So anyway, zinc can kick out the hydrogen, so now it's bonded to chlorine, and because zinc has a 2 charge and chloride only has a 1 charge, the formula is going to be ZnCl2. And then hydrogen's by itself is the pure element, which is going to be H2 because it's a Hunkelbrief. The next example we have gold trying to kick out the hydrogen. Now this will not occur because, or this reaction can't happen because gold is actually less active than hydrogen. So hydrogen's going to want to bond to the chlorine more than the gold could. In the next example, we have sodium thrown into water. Now sodium is a very active metal. It's in the very top, one of the top elements in the activity series, so it can successfully break this hydrogen-oxygen bond. But what's kind of interesting about this reaction is it doesn't make sodium oxide, it actually makes sodium hydroxide. And to visualize this, we're going to write the formula for water as HOH. That's hydrogen hydroxide. It's still water, but you can kind of see what's switching. Sodium is only kicking out the first hydrogen in the formula. So now sodium is bonded to the OH group. They are electrically neutral, +1, -1, and then hydrogen is the diatomic elements. Now in this example that I used right here with sodium thrown into water, this is what I nicknamed the Beethoven reaction when we were balancing chemical equations. So if you wanted to balance it, you could with 2221. In the next example, we have iron thrown into water. Now this reaction can't occur because iron is not active enough to replace hydrogen in water. Now it could replace hydrogen if it were an acid, but since it's hydrogen in water, this switch cannot occur. It's got to be one of the top active elements on the list, from lithium to sodium, on the activity series for the reaction to occur. And so iron is not active enough to make the switcheroo occur. In the last example, we have copper trying to switch with silver. Copper is higher than silver, and so it now bonds to the NO3 group, and then silver is the pure element by itself. The charges on copper, I'm going to make it as a +1 charge, and then nitrate is -1, so the charges work out. If you look at a visualization of what this reaction would look like, here's kind of what it looks like. We have a stick of copper thrown into a solution of silver nitrate, and what happens is that the copper dissolves into the solution and the silver comes out of the solution, and that's the substance that's growing on the outside of the copper. So the copper disappears into the solution, the silver comes out. That's called a single replacement reaction, and it occurs in an aqueous solution. On the next slide we have reaction number 4, and it's called a double replacement reaction. It's sometimes referred to as an ionic reaction, but I like to call it double replacement. It's a reaction between between two compounds that are dissolved in water, and it produces two different compounds, and one of the compounds is going to be insoluble, or it could be water or a gas that doesn't dissolve in water. But one of those compounds is going to go from being aqueous to not aqueous. Here's what the general form looks like. We have the compound AX, which is aqueous, BY, which is aqueous, and then we do the little switcheroo like we did in the single replacement reaction. Now A is bonded to Y, and B is bonded to X, and in this example I have BX being the precipitate, or the solid compound. Here's what it looks like in terms of the colored spheres. Now, you must use the solubility chart to see which product is the precipitate. The solubility chart is a table in our textbook on page 887, and it has little letters that are in a table which indicate what substance does not dissolve in water or which substance does dissolve. So capital I means insoluble, or the little SS means it's slightly soluble. For our examples, we're going to consider it to be the precipitate. The other letters that are in this table, which I don't have a picture of in this presentation, but the students get a copy of it. The other letters would be a letter D, which means it decomposes in water, and we're never going to use that. Or there's a little slash mark, which means the compound doesn't exist, like silver hydroxide doesn't exist in nature. And there's also a capital S, which means it's soluble in water. So if you see I or SS, that's the precipitate. If you see the regular old capital letter S, that means it's soluble. So let's do a couple examples to kind of get the handle of what things are switching. Here we have calcium chloride and silver nitrate solutions. We're going to throw them together and switch the fronts. So we're going to switch the calcium and the silver. So now calcium is going to be bonded to the nitrate group, and silver is going to be bonded to the chloride group. Now calcium has a 2 charge where nitrate only had a 1 charge. That's why it ends up being a formula of CaNO3 parentheses 2. And then silver and chloride have +1 and -1 charges. And again, if you're worried about balance in the equation, you could do that later. Now we're going to use the solubility chart and look up which one of these compounds forms the precipitate. All nitrates dissolve no matter what compound they're stuck with or what metal they're stuck with, so that's going to be aqueous, and the silver is very rarely soluble, and so the silver is going to form the precipitate. And I'm going to use the symbol that we had in the first lecture, the arrow going down, which represents the solid precipitate. In the second example, we have the hydrogen and the sodium switching places, and now hydrogen is with the hydroxide group and the sodium is with the chlorine group, or the chloride group. Now sodium chloride is obviously aqueous because that's just plain old table salt, and then water is going to be the hydrogen hydroxide compound, so it's H2O, which is a liquid. So switching the fronts is the technique we use for the double replacement reactions. Now, like single replacement reactions, you had to look up on the activity series that the switch actually occurs. In double replacement reactions, you don't have to do that. The switch automatically occurs, and you're going to have some precipitate being formed. So you only have to use the solubility chart to see what the precipitate is. You don't have to use the activity series to see if one metal's more active than another. Here's what a double replacement reaction would look like. You have one solution being poured into another solution, and then you have a precipitate or a cloudy substance. In this case, it's a yellow substance that forms, and that cloudy substance is the solid, and it would sink to the bottom, and you could filter it out if you wanted to. The other compound that exists in the solutions is soluble, so it's invisible to the naked eye. If you wanted to, you could filter out the yellow substance. You could take the leftover liquid and evaporate all the water, and then you would get the other compound to crystallize out of the solution. The last type of reaction is the easiest one of them all. It's called a combustion reaction, and it's a reaction between a compound that contains hydrogen and carbon and hydrogen, and sometimes there's oxygen in the compound. But it's basically a carbon-hydrogen compound. You're going to burn it, so you have to react it with oxygen, and the products are always the same. It's CO2 and H2O. So it's the easiest reaction of them all. It doesn't matter how many C's and H's and O's, you always make CO2 and H2O no matter what. The toughest thing about this type of reaction is balancing it. Now, the last part of the notes deal with what we call writing a net ionic equation. And the net ionic equation is only used for double replacement reactions in first year chemistry. Basically, the net ionic equation only shows the ions that were used to make the precipitate. The other ions, which don't do anything, they stay dissolved in the water, are called spectator ions. Kind of like if you're a spectator at a football game, you're not a participant in making the precipitate, you're just watching it. So the spectator ions you don't need to worry about. So let's take a look at this example. Everything that's that's aqueous is composed of ions. So we have calcium ions, and we have a couple chloride ions, we have a couple silver ions, we have 2 nitrate ions, and then on the right side of the equation we still have calcium ions, we still have 2 nitrate ions, but now we have a solid precipitate, the silver chloride. So there are some ions that stayed aqueous on the left and they're aqueous on the right. So those are the spectator ions, and we don't really need to show them because they're not doing anything. So we can cancel them out, and what you're left with is what we call the net ionic equation. It only shows the ions that make the precipitate. Now I happen to have it balanced with 2, 2, and 2. That's just because up in the above equation we had to balance it with 2's. But technically, since they're all 2's, I guess you could cancel them out if you wanted to and make it 1 to 1 to 1. On the next page, I do it a little quicker canceling out process. So let's form the precipitate. If we switch the fronts, which is barium and the potassium, you get potassium with the nitrate group, and you get barium with the carbonate group. Now one of these compounds is always soluble, and one of the compounds always makes a precipitate. The nitrates are always going to be the soluble part, so that's going to be the aqueous part, and then the other one has to be the precipitate. So let's look at what ions stayed aqueous on the left and aqueous on the right. Well, obviously it's going to be the potassium and the nitrate, so we can cancel out the potassiums because they don't do anything, and we can cancel out the nitrate ions because they don't do anything. And what you're left with is what we call the net ionic equation, the ions that make the precipitate. So we have the carbonate ion, it has a -2 charge, it's obviously aqueous. We have the barium ion, it has a +2 charge, and again it's obviously aqueous, but when you form the precipitate it makes the solid. So that's basically how you write chemical reactions in predicting the products.